Hello friends, welcome to the next lecture on cosmological perturbation theory. In this lecture we are going to look at the next steps of the transformation of 0 to rank tensor f alpha beta. So gauge transformation of f alpha beta, and this we derived an expression for the gauge transformation of f alpha beta for the perturbation in f alpha beta from one gauge to another gauge, and this is what we got in the last lecture. We have delta f alpha beta in gauge 2, this is in gauge 2 and this is in gauge 1, delta f alpha beta. So we are dropping heads. When we introduced gauge 1 and gauge 2, we kept caret on gauge 1, tilde on gauge 2, and from now onwards we'll drop carets because we are already differentiating the background gauge with the bar on top. So background gauge will have bar on top, gauge 2 will have tilde, and gauge 1 we are dropping the carets from top, and we'll be having we'll call it without caret sign. So we have delta f alpha beta in gauge 2 is equal to delta f alpha beta in gauge 1, and then we have all these terms which we looked at in the previous lecture. Now we also saw that f bar alpha beta respecting homogeneity and isotropy will be of this form. There will be TT component, eta component, XX component will be same as YY component, will be same as ZZ component. So f bar alpha beta will look something like this. An example of f bar alpha beta is the metric tensor G alpha beta, G mu nu, which you have looked at in general relativity and in the standard model of cosmology. And we also have energy momentum tensor T mu nu. In G mu nu we have, by the way, this A, do not confuse it with the scale factor, it is just an arbitrary constant. In G mu nu we have A square T minus A square T as eta component. TT component is minus A square T, XX component is A square T, and then A square T, and then A square T. So minus A square T, A square T, A square T, and A square T. And in energy momentum tensor, we have in the 0, 0 component, we have density, and XX, YY, 1, 1, 2, 2, and 3, 3 component, they are pressure. You can also write if you look at this term, you can see that the second term of this equation, f bar alpha beta, it does not vary in spatial direction. Derivative of f bar alpha beta varies only with respect to the conformal coordinate eta. Respecting homogeneity, there is no variation in the spatial direction, because respecting homogeneity, its partial derivative with respect to a spatial coordinate will be 0. So if we want to contract it on gamma, then only the 0, gamma equal to 0 will survive, and spatial derivative of f bar alpha with respect to 1, 2, and 3, they are 0. So this simplifies to this. And also we can write the spatial part of this matrix as Fij, the spatial components, and this is the spatial part. B, B, B are the diagonal elements. So we can write this as B delta I J. And what is B? If you notice that B is sum of F11, F22, and F33. So we can say that 3B is sum of F I 3B is sum of FKK. Therefore, or you can write it as FKK. So either you write it one index upper or lower, or both indices lower in three-dimensional space. In three-dimensional metric, the metric is delta ij, and it doesn't matter in which whether you write indices on top or at the bottom. Lower or upper indices position doesn't matter in three-dimensional space. But if you want to respect the proper proper tensor notation, then you may like to write it like this. Some textbooks write it like this. Remember that if you come across in this form in three-dimensional space, and remember that you need to contract on this repeated elements in three-dimensional space. So if I have Fii in three-dimensional space, both Ii are on the lower side, I need to contract, even if it is not written in this form. And that is because the metric tensor is delta ij. So from here, you can come to here by applying delta ij, this by using this metric tensor. Okay. Next, therefore, we can write this B as this divided by 3. Okay, this is the recap of the previous lecture. Now we would like to, before I go further, let me rewrite this equation. This will be this. Second term is this. And rest is okay. 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 Now next write the various elements of various components of this delta F alpha beta. Let us start with the 0 0 component. 0 0 component. So we can write 0 0 component as this is 0 0 0 0 0 0 and alpha is 0 and then beta is 0 and alpha is 0 and then beta is 0. Okay, so what is this? Only 0 component survives from here and only 0 component survives from the last term. So the third term and fourth term, only the 0 component survives because the metric is because the tensor is diagonal. So I can write this as only 0 component survives. Only 0 component survives. Only 0 component survives. And 0. So further simplification will lead this to 2 times this. So this is the 0 0 component. Now next comes the 0i component, and you can easily see that 0i component is same as I0 component. So they both are same here. If you have one index upper and one lower, like if you have delta F with alpha upper index, beta lower index, then 0i component and I0 components, they will not be same. In that case, you need to calculate the two separately. But in this case, when both are on the lower side, on the same side, 0i will be same as I0. So we can write alpha is 0 and beta is I. Okay, alpha is 0 and beta is I. Alpha is okay. Let's see what terms we can simplify. F0i. This is 0 because 0 is the time component and I starts from 1 to 3. So F0i is 0. We can eliminate this. Now here only the 0 term survives. So I can write 0 here and 0 here. Here also only the, mu I, yeah. Here only the item will survive. Yeah, only item will survive here. So we have mu. So this, when this contracts, only So when we contract this here, zero term will vanish, and we can say that other terms are uh, 1, 2, and 3. So I can say that zero term, after eliminating zero term, I can keep the rest of the terms, and I can say j here. So 0 is gone. Now 1, 2, 3 are still left here, and f bar ji, or you can write it as f bar ij, that I can write in this form, beta delta ij. So I can write f bar ji as beta delta ij, this, and this 1 by 3 delta ij. Right. So 1 by 3 delta ij, j will contract, and we have this. Or you may like to write it in this form if you like. So this is what we get for 0i. You can go one step further and see that here contracting j, you can write this as xi I, like this. Now xi I is in three-dimensional space, Euclidean space. So xi I is in 3 Euclidean space, and in 3 Euclidean space, whether you put I on top or I on the lower index, it will be the same. And if you want to respect the tensor notation, I is a lower index here. Therefore, you can keep I as a lower index here, like this. In tensor notation, the values will be the same. So in tensor notation, remember 3 vector, because metric is delta ij, so upper index, lower index values are same. In three-dimensional Euclidean space. Or if you like, you may call it some general vector, any vector, bi or bi, any vector. This applies to any vector. Okay, so yeah, so this is a final expression, I think, as far as we can go with the 0i or I0 component. This is what we get. Now let us look at ij component. Okay, ij component. Okay, let's start from here. So we have ij, then we have ij, then we have ij, then we have I. Take a breath, and then j. And then we have I. Take a breath, and then j. Okay, now f bar ij, we can put it in the form that we just learned, and it's this beautiful form, this form here. Before I write Fij in my favorite form, which is this form 1 by 3 delta ij fkk, I can first look at the last two terms. In the last two terms, notice that zero component will vanish, f bar I0 and f bar 0j will vanish, and only the special components of f bar, special part of new new index and mu index here will survive. So we can do one simplification here, that I can write this as k and k because zero component vanishes. So I can write this as k and k. And now I can write this in that form, 1 by 3 delta ij form. So we can write this f bar and this f bar in this form. But before that, I forgot that this in this term only the zero component survives, and this we looked at before we started looking at the components. Only the zero component survives, and that means this is let's double check. Yeah, only, yeah. So here, because there is no change with respect to the spatial component, so only zero component survives here. Okay, now we can write all ij, f bar ij, this f bar ij, f bar ik, and f bar kj in this form, 1 by 3 delta ij form. So f bar ij will be 1 by 3 delta ij f bar kk. Actually, I can write f bar kk here. write like this, bar kk with respect to 0 and 1 by 3 delta ij. Then we have 1 by 3 delta ik by 3 delta ik, and this will be f bar, you can say LL and then again this will be f bar kj will be f bar LL. If you like, you can now combine, factor out FLL from the last two terms. So 1 by 3 FLL we can factor out. Like this. This is positive sign here. And we can say this is EI, sorry, Xi I, and this is Xi J. Delta so Xi I derivative with respect to j plus Xi j derivative with respect to I. Yeah, and this is not minus, but this is f bar. So we have f bar LL Xi ij plus Xi ji, and any further simplification we can do. Let's see. Yeah, so I think that's it. And again, if you want to see ij in proper index tensor notation form, you can bring this I down. Can bring this I down and this j down, because they are spatial indices, and in spatial index, in spatial coordinate system, the metric is delta ij, and you write up I, down I, it's the same. Upper index or lower index, the value is the same. Now you have in proper tensor notation both ij in lower index. Okay, so these are the components of delta f alpha beta 0 to rank tensor. We have 0 0 component transforms by this relationship from gauge 1. This is gauge 1, this is gauge 2. 0 and I0 component transform according to this relationship. And remember that if your perturbation, perturbation tensor is in the 1-1 form, then you have to calculate 0 and I0 component separately. But here, since they are both on the lower side, 0-2 form, we can calculate only 1 0i, and that will be same as I0. So we have three scenarios: 0 0 component scenario, 0i, I0 component second scenario, and then third scenario is IJ component. We can write this as KK, change the index from L to K to keep it same as this. Next, we can look at the trace and traceless part of this matrix. It is a 3 by 3 matrix, delta Fij. Delta Fij is a 3 by 3 matrix, and let's see what the trace part and traceless part of this matrix looks like. So, trace part of delta Fij is of this form, 1 by 3 delta Fij, and delta F LL. It is not 1 1, it is LL. It looks like 1 1. I can write here MM. Okay, so trace part of delta Fij is 1 by 3 delta Ij delta F MM, and we need to repeat over, we need to sum over this repeated indices. Okay, so you may ask that why have I not written 1m on top and 1m on the lower index like this? We at this point, until we calculate delta Fi top, I on upper index and j on lower index, I would not write it as m on top index and m on lower index, because I'm not sure at this point that delta F with m upper with I upper and j upper is same as delta F with I lower and j lower. So we will see maybe in the next exercise that how does delta F with I upper and j lower looks like. Is it same as uh, delta Fij? That part I can know. I can tell you now. It is not same as delta F with Ij lower. But what about delta F M upper and M lower? I am almost certain. We will calculate in the next exercise, but I am certain, almost, that that will not be same as delta F MM because of the way we are calculating this perturbation. So I'm not writing it. So I'm not writing with the M top and M bottom. I'm writing both M and the lower indices. Okay, but remember we need to repeat over lower indices. So, okay, so what is the trace part of this? Trace part of this is this, and this is equal to so trace part of delta Fij is this. Now let us see what is the trace part of delta Fij tilde looks like. Trace part of delta Fij tilde Fij is this. This. Okay, and by the way, trace part of delta Fij is this, and traceless part of delta Fij is delta Fij minus this. Trace part of delta Fij tilde is this, and can we simplify this? Let's see. Okay, 1 by 3 delta Ij delta Fmm. Let's copy this expression. Okay. 1 by 3. Need to bring it here. This and this, and this is mm. Okay, and this is mm. Okay, this is m xi m with respect to m, and next is also xi m with respect to m, so this is mm. And remember, you need to sum over repeating indices, so this is xi1, derivative of xi1 with respect to 1, xi2 with respect to 2, xi3 with respect to 3, sum of all of those three terms. Okay, so we have, what is delta mm that we can further simplify? I can further simplify this. Delta mm is 3, delta 1 1 plus delta 2 2 plus delta 3 3. So this becomes this. Okay, so this is the trace part of delta Fij tilde. Now, what is the traceless part of delta Fij tilde? Traceless part of delta Fij tilde is traceless part of delta Fij tilde is this. Need to replace delta Fij with delta Fij tilde here, and this is this. Okay, this is the traceless part of delta Fij tilde. Now we can subtract this, so minus 1 by 3, this is trace, and this is the traceless part. So this is minus, okay, this is the trace part, and I need to write expression for delta Fij tilde also, which is this. Delta Fij is tilde is this. Minus here and here. Okay. Now from here, let's see what we can simplify. We can see that this term and this term vanishes. They cancel each other. Okay. So now we have what do we have? Now we have yeah, so we can combine this Fij minus this part here, minus here, delta Fij minus here, like this. So we have delta Fij, this is traceless part of delta Fij. Okay, and we are doing the traceless part of delta Fij tilde. So this is gone, it comes here, and now this is the traceless part of delta Fij, and I can factor out f bar 1 by 3 f bar kk here. So I get this xi I comma j plus j comma I plus delta ij minus delta ij 2 by 3 f bar is here. Can do this. Now notice that this is a matrix which is traceless. Why do I say that? See, I can write this as this can be written as sometimes this formatting takes a lot of time. Sometimes it's easy, but overall typing in Mathematica is fun. Okay, so I can write, let us consider this part only first, or maybe you can leave, type this 1 by 3 and this also 1 by 3 here. This and this. These two are two matrices. Let us say this is Aij and this is Bij. So this is a matrix, say it's a 3 by 3 matrix, is a 3 by 3 matrix, 3 by 3 matrix, and if this is a 3 by 3 matrix, let's say that this is Xi is a 3 by 3 matrix, and this is the with it's a 3 by 3 matrix with trace equal to this. So this is trace of this. If I say this is Aij, this will be 1 by 3 delta Ij AMM. If I say this is Aij, this is AMM. And so this is trace of this, and therefore this is traceless. And this is the traceless part of Xi Ij. Right? Therefore, this whole this matrix or tensor, which is inside this brackets, is traceless. Because when I split this into two parts like this, and I see that this is the traceless part of this, and this is the this is the trace part of this. So this is traceless, and this is trace part of this. So this whole is traceless, and overall it is a traceless matrix. And you don't have to split this into two parts. You can say that for a matrix, even without splitting, you can say, or you can see that for this matrix, for this tensor, the trace is this. Because this is, if this is Aij, trace will be 1 by 3 delta Ij, which is this part, AMM, and AMM will be Xi m derivative with respect to m plus Xi m derivative with respect to m, which will be 2 times Xi mm. So we get 2 by 3 delta Ij Xi mm. So this is, the trace is this, and this is traceless, and therefore this is traceless. So overall this is traceless. Therefore what we can say is that the traceless part of delta Fij tilde is equal to the traceless part of delta Fij. This is a traceless part of delta Fij plus the traceless part of this. traceless. This. Thank you for watching this video. See you next time. Bye bye.